Section 20.3 Electronic Spectra of Atoms. Subsection B The Classification of Microstates. When we have two electrons in the 5 different d orbitals, there are 45 microstates. This is because there are 10 options for electron 1 and only 9 options for electron 2. Therefore, we have 90 options if these two electrons are distinguishable. However, electrons are indistinguishable. Therefore, we need to divide 90 by 2 factorial, the number of permutations of 2 electrons. And 90 over 2 factorial is 45. So we have 45 microstates for the 2 d electrons in the 5 d orbitals. Now we'll group these 45 microstates into 5 atomic terms that are spectroscopically distinguishable. That means in the atomic spectrum of this atom with 2 d electrons, we'll be able to tell that there are 5 different atomic terms. Now, how do we group those microstates into atomic terms? We'll have to look at 2 different quantum numbers: the spin quantum number and the orbital quantum number. What we need to do is we need to sum up the spin momenta of these 2 electrons together. We need to sum up the orbital momentum of these 2 electrons together. And then if we're talking about individual electrons, we use m sub s as the quantum number for the z component of electron spin. Again, when we are talking about individual electrons, we use m sub l as the quantum number for the z component of its orbital angular momentum. Now we have 2 electrons. We need to look at their collective behavior. That's why we need to sum up their z components of the spin and the z components of their orbital motion. So you may ask, why don't we just add up the 3-dimensional spin and 3-dimensional orbital motions? Why do we need to look at the z components? Well, if you look at the z components, they are scalars. It's easier and much more convenient to add up those scalars. And now if you look at the 3-dimensional spins, 3-dimensional orbital motions, they are vectors. It's much more difficult to add up vectors together. So now let's look at the z components. We have 2 electrons. And then we can write out the possible values of m sub l for these 2 electrons, from -2, -1, 0, 2, all the way to 2. So 5 different possible values. Okay? And now we can put the 2 electrons into this orbital. And then the sum of m sub l is going to be -4, because each of the 2 electrons has a m sub l of -2, and we have 2 of them. Now if we put these 2 electrons in the same d orbital, they have to have different spins. So one spin up, one spin down, the sum of m sub s is going to be 0. Alright, so this z component is positive half h bar. This one is negative 1/2 h bar. Together it's 0. So that's how we get the first combination of the uppercase m sub l and the uppercase m sub s. Alright, this is the first microstate. Now I want to remind you, for a single electron, we use lowercase m sub s, lowercase m sub l. For a multi-electron atom, when we are grouping their microstates together, we use uppercase M sub L and uppercase M sub S as the sums of the lowercase m sub s and the lowercase m sub l. Now let's look at the second microstate. Now this time, still, I'm going to have one alpha electron, one beta electron. This alpha electron is in this -2 orbital. This electron now is in the -1 orbital. So the sum is -2 plus -1. It's -3. What about the spin? 1 alpha, 1 beta, positive 1/2 h bar, negative 1/2 h bar. The sum is just 0. The third microstate, here and here, the sum of m sub l is -2 plus 0, it's -2. The spin, 0. Now -2 and positive 1. So we have -1 here with a spin, the sum of the spin to be 0. And then again, 1 alpha, 1 beta, -2 plus 2. Together you have 0 here and another 0 for a spin. Now I'm going to change the way of arranging these two electrons. Now it's the beta electron in the -2 orbital, alpha electron in the -1 orbital. And then I get -3 and 0. Alright? And then we have alpha beta both in this -1 box. The total is -2, the spin is 0. And then we have -1, 0, etc., etc. Alright, so you just keep doing this until you finish enumerating all 45 microstates. Right, so all 45 are here. And then I'm going to color this 45 microstates. And I will delete this 5 columns. These 5 columns are useful for us to just determine the sums of lowercase m sub l and m sub s. Once we have those m sub l, m sub s, the uppercase ones, for the 2 electrons, we can remove these 5 columns. Right? This is just a tool for us to determine the set of values for uppercase m sub l and m sub s. So again, 45 microstates, and now they are colored. I will tell you why they are colored. The red ones belong to one atomic term. The yellow ones belong to a atomic term. The blue ones can be assigned to one atomic term. Same for the green ones. And over here, the purple can be assigned to one atomic term. So 5 colors, 5 atomic terms. Red, yellow, purple, blue, and green. Alright? So 45 microstates. So how did I get those colors? How did I choose the microstates in red color? Well, very simple. You look at these 5 microstates. You look for the largest m sub l. And that's going to be the quantum number L for this group of electrons. Okay, the largest m sub l. The reason is pretty simple. If you remember, in general chemistry, this m sub l can be from -L to positive L. So the largest m sub l is equal to the value of L. Alright, so I want to put the rule here. It's between -L and -L plus 1, etc. And then L minus 1, and then L. That's the rule. Okay, that's the rule. So now we can see this m sub l can adopt different values, but the largest value is the value of L. So we're going to look for the largest m sub l. We look at this table. We find the largest m sub l is, well, I don't know. Over here, maybe 4. Okay? 4. And then you look for all the rows that contains M sub L being 4. Actually, there's only one row, so I'm not going to show you the entire table anymore. And then look at its M sub S. It's 0. Alright, so only one row, M sub S, can only be 0. Now you need to look for the other rows with M sub S equals 0. M sub L should be a series of numbers from negative 4 to 4. So again, this is the largest M sub L. And that tells us the value of L is 4. And when L is 4, the possible values of M sub L is going to be negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. 9 of them. So you need to find all 9 microstates. So 1, 2, 3, 4, 5, 6, 7, 8, 9. All 9 of them. Alright. You may ask, there is negative 1, 0, and also there's negative 1, 0. Which one should you pick? It does not matter. It does not matter. Just pick anyone. So you can color this red, but then you need to color this yellow. It doesn't matter. Why? This way of grouping microstates does not really have a physical meaning. It does not really correspond to the actual wave functions of those microstates. This is just a tool of determining this atomic terms quickly. So you get 9 rows in red. They are not 9 microstates that correspond to L equals 4 and S equals 0. Why S equals 0? Because M sub S can only be 0. That means S has to be 0. So I'm going to write out the other rule here. This is M sub S. M sub S can only be from negative S plus 1, and then negative S plus 2, etc., etc. So the values between negative S and positive S with an increment of 1 every time. Alright, so that's how we do this. Okay. And again, that's why I just, colored this 9 rows in red. It's just easier for us to clearly see that we can assign this 9 microstates to a atomic term. This atomic term has L equals 4, S equals 0. And now we need to write out the term symbol. It's 1G. Why 1G? So remember, when L is 0, 1, 2, 3, 4, the symbol is S, P, D, F, G in general chemistry. In here, we use the same convention. When L is 0, 1, 2, 3, 4, we have the symbol to be S, P, D, F, G. So in this case, L is 4, the symbol is G. However, for a group of electrons in an atom, we use uppercase S, P, D, F, G. For a single electron, we use lowercase S, P, D, F, G. So that's why you see this uppercase G here. What about this number? This number is actually the spin multiplicity. We'll get back to this later. But for practical reasons, I'll just tell you this number is just 2s plus 1. When s is 0, 2s plus 1 is 2 times 0 plus 1. It's just 1. And it's a singlet. So really, it means all electrons are paired, and then there's only one possible spin multiplicity. All right. Now we need to delete this 9 rows from the table of 45 microstates. So 45 minus 9, we have 36 left. And then what you need to do is you again look for the largest m sub L. It's going to be the value of L, and then find all possible values of m sub L from negative L to positive L, and each of them should have the same set of spin values as the rows of the largest m sub L. The reason I put this S here because, well, sometimes you can find multiple rows with the largest m sub L. So in this case, let's look at the original table here. Just imagine we deleted those red rows, and then the largest m sub L is going to be 3. So you see this 3 here. The corresponding m sub S is 0. But this is not the only 3. I think you can find 2 other 3s. 3 and 1. So m sub L is 3. M sub S is 1. There should be another 3. 3, negative 1. So really we found 3 rows with m sub L being 3 and m sub S being negative 1, 0, and 1. So we are looking at now not just one value for m sub S. We have a series values for m sub S from negative 1 to 0 to 1. That indicates the spin number S is equal to 1. Because when S is 1, m sub S can be negative 1, 0, and 1. Now let's look at some other rows and see if we can find a series of m sub L as well. So when m sub L can be 3, the largest value of m sub L is 3, that means L is 3. When L is 3, m sub L can be from negative 3, negative 2, negative 1 to 0, and then 1, 2, 3. 7 possible values for m sub L. And we learned that there are 3 possible values for m sub S, negative 1, 0, and 1. And these 2 series are independent of each other. So you get 7 options for m sub L. You have 3 options for m sub S. In total, you have 7 times 3 options, 21 options, or 21 microstates. So you just look for this 21 microstates. And I colored all these 21 microstates in yellow. So 21 of them, right? Okay, there are 21 of them. And again, you may ask negative 2, 0, negative 2, 0, which one is red, which one is green, which one is yellow, which one is green. It doesn't matter. Again, this table just provides you a convenient tool to determine the atomic terms. But individually, this negative 2, 0, this negative 2, 0, well, they do not tell you any information about the actual wave functions. So that's why. All right, so again, we'll find 21 of them. You have 4 here, 3 here, so 7 plus 4, 11, 11 plus 7, 18, 18 plus 3, 21. So you have actually a table, a 7 by 3 table. You have 7 rows of different m sub L values and 3 columns of different m sub S values. Alright, so it's a 7 by 3 table. Okay, 7 by 3 table right here. And then because m sub L can be from negative 3 all the way to 3, then L has to be 3. M sub S can be from negative 1 to 0 to 1, that means S has to be 1. So now we have this atomic term with L being 3, S being 1. The atomic term symbol is 3F. So again, when L is 0, 1, 2, 3, we have SPDF. So it's F here. And we use uppercase for a group of electrons in an atom. This is 2s plus 1, so 2 times 1 plus 1 is 3. That's the spin multiplicity. So we call this a triplet spin multiplicity. Why it's a triplet? Basically, it's either alpha alpha beta beta, or alpha beta plus beta alpha. All right, so a linear combination of alpha beta and beta alpha with a plus sign. All right, so it's a triplet spin multiplicity. And then you delete this 21 microstates from the table as well. We deleted 9, then now we delete 21. So 45 minus 9 minus 21, we have 15 left. We have 15 left. And then what do? We find the largest M sub L from this remaining 15 rows. And then we determine this 1D atomic term, with L being 2, S being 0. Okay, 5 of them. And then we delete this 5 microstates. We find the largest M sub L in the remaining 10 microstates. And we come up with another table, a 3x3 table. This L is 1, S is 1. So M sub L is from -1 to 0 to 1. M sub S is -1, 0 to 1. The term symbol is 3p. Again, when L is 0, 1, 2, 3, the symbol is SPDF. And we use uppercase for atomic term. This 3 is 2s plus 1. Finally, there's 1 microstate left. L has to be 0, and S has to be 0. And then the symbol is 1s. So in total, we determined this 9 microstates in red is our 1G atomic term. And over here, this is 3F, this is 1D, this is 3P, and this is 1S. A total of 45 microstates. So now you know it's really tedious to determine the 45 microstates and then group them into 5 atomic terms. But there is a really easy way to determine the 5 atomic terms for the D2 electron configuration. So I'm going to show you this table. In this table, it's actually M sub L and M sub L in the rows and in the columns. All right, in the rows and in the columns. And then we're going to put the electrons into those boxes. Over here, this means both electrons have -2 as the value of M sub L. All right, both electrons. So that means they are in the same d orbital. That means, well, they have to be 1 alpha and 1 beta. No other exceptions. So actually, there's only 1 microstate here. -4 is the sum of the values of M sub L of these 2 electrons, -4. Now let's put 1 electron in -4, the other electron in -1. In this case, these 2 electrons can have the same spin. They can have different spins. So I put 4, -3 here. Why -3? -2 plus -1 is -3. Now we have 4 spin options. We can have alpha alpha, alpha beta, and beta alpha. But really, if you took quantum mechanics, you need to do linear combinations of alpha beta and beta alpha. Alpha beta plus beta alpha is one of the triplets. Alpha beta minus beta alpha is the singlet spin. So just for determining the atomic terms, we don't have to worry about that. You just need to put 4 -3s in this box. Same here, 4 -2s, 4 -1s, 4 zeros. Again, we get 4 zeros because we have 2 electrons, one with -2 M sub L, the other +2 M sub L. The sum is 0. And then let's look at the spin. They can be alpha alpha, beta beta, alpha beta, beta alpha. That's why we put 4 numbers here. And similarly, we fill out all other tables. And because the electrons are indistinguishable, we do not have to fill out the upper triangle. And again, do not fill out the upper triangle because electrons are indistinguishable. All right. Now let's look at this lower triangle. And then look at the 9 numbers in red. Alright, on the 9 microstates that belong to the 1G atomic term. Okay, so you have this 9 and delete this 9. And then look at this yellows. Alright, the yellows. Alright, the first column and the bottom row. You see 21 microstates. They belong to the 3F atomic term. Okay, and then delete the yellow. You have a smaller table. You find this 5 greens. That's 1D. The 3 by 3 microstates. That's 3P. And finally, it's 1S. Actually, using this table, you can also determine the atomic term symbol for S2, P2 easily. So this is just a 1-by-1 table for the S2 electron configuration. And over here, you're looking at a 3-by-3 table for the P2 electron configuration. So if you have a P2 electron configuration, the atomic term symbols are 1D in green, 3P in red, and 1S in purple. And now you have this 5-by-5 table for the D2 electron configuration. What about F2? Well, it's pretty easy. For F2, you just need to add 2 columns and also 2 rows. You need to expand this M sub L. You need to include -3 here and +3 here. Also, you need to include 2 more rows, -3 and +3. In that case, you have a 7-by-7 table. You get 7-by-7 table. And then the largest M sub L is going to be 5. And then you use the same algorithm. Okay? It's just for a 7-by-7 table. I'll let you imagine that. Okay? And then the first atomic term is going to be 1I, singlet I. Alright? S equals 0. So 2S plus 1 is 1. It's singlet spin multiplicity. And what I? Well, I means, well, S, P, D, F, G, H, I. Alright? I means L equals 7. So you have 1I. And then you have 3H. Okay, 3H. So H means L equals 6. So this L is 6. M sub L is -6. -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, 6. 13 possible values for M sub L. Right? And this is 3H. And then you have this 1G, 3F, 1D, 3P, and 1S. You probably see the trend already. If you have S2 electron configuration, it's just 1S. Now if you have P2, 2 electrons in the p orbitals, you have 1S, 3P, 1D. What if you have the D2 electron configuration? 2 more atomic terms, 3F, 1G. Now what about the F2 electron configuration? Well, you need to add 2 more atomic terms, 3H and 1I. Okay, so I can write out the atomic term symbols for F2 in 5 seconds. You just write S, P, D, F, G, H, I. And then you add the superscripts 1, 3, 1, 3, 1, 3, 1. You're done. You're done. So what if you have the more complicated G2 electron configuration? You have 2 electrons in the G atomic orbitals. Well, just 2 more atomic terms after I. After I, it's not J, okay? So I think one reason we do not have J in the atomic terms is there's no letter J in the Greek alphabet. It could be one of the reasons. So after I, it's actually K and L. And then you have 3K and 1L as the atomic terms for the G2 electron configurations. when you have 2 electrons in the g atomic orbitals.